Good morning, everybody. My name is Nick Andrio. I'm the VP at Production Modeling Corporation, and I have the pleasure of speaking to you this morning about what we call smart communities. Today's discussion is about smart factories, but what we have been recognizing over the last few decades that PMC has been in this business is that what we have been discovering in smart factories also translates to smart communities and eventually smart cities. So we're going to be talking through how the components of these various pieces work together. So let's take a look. When we have been looking at digital twins and developed this expertise over the years, some of the components included laser scanning and creating 3D BIM models, building information modeling objects, doing our different simulations such as process flows and simulations of man and machine, flow of parts. This has been a factory, smart factory type of work. But when we look at how this also applies to communities, the same components seem to work. In other words, we laser scan, create BIM models. Instead of moving parts, we're moving people and transportation, simulate how the systems work, and manage things such as energy, optimize equipment usage. So the language that we have for smart factories and communities seem to make a lot of sense and work together. Today, we're going to have a couple other speakers also join us. I'd like to introduce Chris Mounce, who is our Director of Digital Engineering. And after Chris speaks, we're going to talk about our simulation work with our Director of Simulation. That's David Stone. A couple more slides before I hand it over to Chris. PMC, Production Modeling Corporation, is made up of about 150 engineers globally. We have three main areas of, we show a footprint. Of course, working from home these days, we are everywhere. Our focus for today's discussion is going to be reality capture and the building information modeling, the industrial engineering core work we do, the simulation of manufacturing and other manufacturing features, as well as simulation of many other types of businesses, and the digital twin. Now, the digital twin title itself has so many different definitions, and it is almost humorous to see how many people try to define digital twin. So we too will give it a shot. We have some solid credentials that brings to the table. I won't dwell on these, but we have a dozen simulation modeling engineers, many CAD and BIM developers, and we provide engineering services to other engineering companies, which I take great pride in understanding that we do high-end engineering, industrial engineering, manufacturing engineering work. Moving on, one of the things that is worth mentioning is that having grown up in Detroit, our base has been, of course, manufacturing, automotive manufacturing. But right now, it's about 50%, and our client base is certainly expanding. So where we were in automotive Detroit, clearly we moved to the EV market as well, which has some similarities and yes, some differences. But we've used our industrial engineering and digital twin knowledge to also simulate things like distribution, warehousing, which is, as everybody understands, a huge piece of today's real world. We've also moved into things like, well, vertical farming, where we have expanded our industrial engineering footprint to take what has typically been a yield per acre and putting it into a vertical 10, 15, 20 rows tall, brings industrial engineers way forward in our ability to change the kind of dashboard that we look at for productivity. The entire shipbuilding military industry, these are cities in and of themselves, and so there's work to be done that we've done in laser scanning as well as efficiencies and throughput. In the work that we've done in capturing reality, we've entirely engaged into a AEC, the architectural engineering and construction market, which Chris will be talking a lot more about here just shortly. And then one of the interesting pieces that we've done is that when we have large multi-site customers, we've done both throughput, discrete event simulation modeling of how to do work here, as well as scanning thousands of these facilities and turning those into BIM models. One of our most recent fun episodes of simulation has been simulating people, large groups of people. How do they move? Where do they move? How much room do we need for them to move? And what happens when there's a panic in a large crowd? So we are one of the primary companies experienced in this area. And so we look forward to expanding this more so here in the US. So we move on. I'd like to introduce Chris Mounts. Chris, if you're available, can you present?
Sure can. Thanks, Nick. Okay, hopefully everyone can see my screen. So yeah, today I'm going to talk a little bit, like Nick said, we have a strong background in digital twins and in manufacturing in particular. And I'm going to talk a little bit about where the state of digital twins are in manufacturing, but understand that this really applies to digital twins in general. It's not just about manufacturing. Really, the whole industry is in about the same place. Some people are a little more advanced, some people are a little further behind. So let's talk about what's happening today, right? And maybe, you know, a definition of what is a digital twin. So I disagree with maybe some of what the industry is coming to. I think that anything in the real world that's digitized into a computer can be called a digital twin. And then what we have are what are the different degrees and different sophistication levels to the digital twin. So let's talk a little bit about what's happening today. So we have lots and lots and lots of good static 3D models being built from laser scanning and in new construction using tools ranging from Autodesk solutions like Revit and factory design to other solutions out there in the NX and CATIA worlds. Are all coming together to build these really static digital twins. These are geometric representations of what's in the real world. Some of those models are starting to get some intelligence built into them and some digital links added to other information. Not a lot, but it is starting to happen. And there's still a lot of research projects going on, and that's where, you know, a lot of people will get confused. They see these really advanced things. Those really aren't deployed yet in tool sets which can be purchased. Okay. So today, like I was saying, we have separate geometric models, and we have, in a lot of cases, we have data models, right? And a data model can be anything from an Excel sheet to a full-on database solution to some of our simulation models that PMC builds. And so what's happening now is the convergence of those data and geometric models into a solid digital twin. Okay. So as we look at kind of the maturity of these twins, and we're going to look at this in a few different ways. We start kind of at the lower end, which is where most people are at, or a lot of people are at today, which is a descriptive twin. You know, basically defining some of the geometry. Things know what they are. A door knows it's a door. A robot knows it's a robot. A window knows it's a window. And then we move our way up into multiple layers of data, and then the holy grail, which is an autonomous digital twin at the end. And these get more and more difficult to achieve while returning higher and higher value to the business. So getting into a little bit of the detail, right? So descriptive is going to be your base model. We're going to generate it with something like reality capture. As we move up into informative, we're going to start attaching some other databases to this. Maybe it's some costing information. It's going to be mostly what we would consider to be static data or data that doesn't change a lot, right? We start to get up into the predictive. Now we're talking about trying to attach some more real-time data, right? So we're linking in our sensors and our IoT devices, and we're combining that into some simulations that are outputting some information for us to act on, right? As we then move up into comprehensive, here's where we're actually going to start affecting the real world from our digital twin. But this is going to be things as simple as maybe setting the temperature on thermostats. This is going to be completely human-driven changes controlled out of the real world and pushed back, or pushed from the digital model into the real world. And then we have this last chunk, right, which is autonomous. And this is where outside of human interaction, changes are being driven by our digital twin back into the real world. A very, very difficult prospect, and one that we all should be very careful about. Okay? So we can kind of simplify this a little bit. We can say you develop your base model, and then you add any kind of layers you want to it of additional data, and then we can add some business intelligence to it. These are applications that are going to start reading, indexing, and analyzing that data and producing other derivative forms for us to try to make better decisions when we're operating our business. Okay. One thing that I think is important to mention is that how we construct these layers, it's not quite as simple as that linear sequence. It really can be any of the three middles can be attacked at any time, and each one of those can have autonomous applications built on top of them, whether that's static information, whether it's IoT information, or whether that's bidirectional information. Different companies will have different needs, and they'll have different starting points. In both cases, you need to start with this core model just so you have a map to attach your other data sources to. Okay. So starting out, talk a little bit about base models, right? If you don't know what you have, which a lot of our customers do not, they do not have a good handle on what they own. It's really hard to do much of anything in the digital twin space. Okay? Base models today are very easy to achieve, right? PMC does hundreds of these a year, or we go out, we scan, we convert it to a model, and it's a nice descriptive model, and there's a lot of ROI on there that we'll get to in a minute. Okay. So we move into informative models, right? We're starting to layer information on the base model. It's simple today to build these models, even though quite honestly, not a lot of people do this. A lot of people do one-offs, they do research projects. There aren't too many companies out there that are truly managing their business this way. It's not hard to do, but it's not done very often. Okay. Now we start getting into the connected models, right? This is kind of a progression from that static data as we start to link in more real-time data. This is also importantly when there's a transition from tool sets. So before this, we're using design and engineering tools that are, things like Autodesk Revit, things like factory design utilities, right? All these things to build in the static data. When we move into connected models, although you can do some strange things with those tools, they're really not the proper tool for it. And there's a lot of different tools out there that will now let us connect this real-time data into our model and visualize it in new and unique ways. Now we get into the predictive models. And these are where essentially we're just taking that data that's coming in from either the static models or the other models, and we're doing predictive analytics on this. So this could be real-time simulation, right, where we're adjusting perhaps our yearly output based on the real-time data coming in from our machines on the floor. Or we could be doing things like adjusting the HVAC levels in a building based on real-time sensor data coming from specific rooms during specific times of day, and maybe mixing that with the future weather forecast, right? So a lot of different things we can start doing with these predictive models. Okay. Comprehensive and autonomous, I tend to link together because these are sort of one and the same. It's really more about whether it's a human triggering these actions or whether it's an autonomous utility triggering these actions. Right, this is sort of the holy grail of digital twin. I can tell you there's extremely limited actual real world applications of this today, but they do exist. There are Everything from fully automated HVAC systems running out there and doing pretty well, to some pretty advanced machine analytics and monitoring that's going on out there. But they tend to be dedicated to a single system and not an entire building or an entire factory or an entire campus. That kind of level of autonomous digital twins are really not happening quite yet. So one thing I want to talk about is that there's value in even the most rudimentary of descriptive twins, and then the value only gets higher as we go up the chain. Descriptive is just something that is easy to do and everyone should be doing today. And so I was going to talk a little bit about that, and the ROI of descriptive twins, right? Again, this is in factories, but PMC has applied this to every industry out there, whether it's construction, medical, all over the map. Just getting accurate 3D information about what you have and then pushing that out to your design and fabrication and construction teams can really have a large impact on the cost of new construction, right? So it doesn't do a lot to lower the ongoing operations of the building, but it can have a lot of impact on the construction and initial first cost of the site. Right? And we lump that together under this title of virtual design and construction, right? And when we can really understand, we can reduce risk, we can reduce the waste on the site, we can eliminate double handling of material, we can do all these interesting things today, and we can really drive some massive process improvements. Okay? In this one, we're looking at a 3D scan of an industrial building and a new HVAC system that's been designed. In this case, we're able to make sure that this actually worked, that the HVAC system as designed and as would be fabricated is going to fit into the factory exactly and not have any interferences. This allows it to be fabricated off-site, shipped to the site, and single-handled to move it up and into installed position. These have real-world cost impacts on jobs. Here's some real data from a large manufacturer that was tracked over time. And in particular, we're addressing field orders. And effectively, we can drive field orders almost to zero, right? So in the first two are sort of our baseline, location A and B, where we're just doing traditional 2D workflows. In 3, we're just updating to a 3D based workflow, and you can already see our field orders are dropping dramatically as a percentage of the base contract. In location D, we switched to what we would call advanced 3D or advanced VDC, in which there were some contractual changes and everything else made, and effectively drive field orders to zero. The only field orders on the project are being driven by actual design changes, not by unknown site conditions, because those have effectively been eliminated. Okay. And the last thing I wanted to end on is actually this from the Digital Twin Consortium. And what this is these are all of the skills. If you're embarking on a digital twin initiative within your firm, these are all of the skills that are going to be required to achieve that top level, call it a level 5 autonomous digital twin. And I think it's important for everyone to understand this. This is not something that one group can spin out on its own. This touches almost every group within your organization. It definitely impacts things like IT and IT security, right? If you're going to roll out an autonomous digital twin, you had better engage your IT security personnel very early, right? It's going to involve all of your business units. These are massive undertakings that are really going to change how your company does business, and it needs to include everyone. And so these projects can be large, and this is just to kind of give you an idea of what's really involved in making that happen. Okay? And with that, that's actually all I have for today, and I'm going to hand it back over to Nick, I believe.
Thank you very much, Chris. Of course, we're going to continue now and bounce over with Dave to talk about the simulation. And I'm going to share my screen and advance to simulation. Dave, are you there?
Yes, I am.
Okay.
Good morning. So I'm Dave Stone. I'm the simulation director at PMC, and it's part of the core services we offer. If you look at our slide here, we offer ergonomic simulation, dynamic and static simulation models, throughput analysis, scheduling, resource optimization, material scheduling, material storage, bottleneck analysis, process simulate. So we are one of the leaders in our industry. Um, just wanted to touch on all the fields that we touch. It's not just manufacturing. It's not just the machinery. With our suite of world-class tools, we have AutoMod, Simulate, Arena, Witness, Siemens, Semio, In Control, AnyLogic. Technomatics platform includes robot and human. These are some of the tools that you'll need for your digitalization of your facility. Um, so why do we do discrete event? It's a process of building a model of a real world system, conducting experiments with this model, and the purpose of understanding the behavior. You work it every day. You're out in the field. You know, the engineers want to do this, they want to do that, and it costs money to make changes. So how do you prevent that? So it reduces costs, reduces time, reduces uncertainty because we build the digital model and it shows the actual production of your system. It increases the accuracy, insights into dynamics that maybe you couldn't see because you're out in the plant every day. It's a risk-free environment. No change has been made. Very inexpensive cost compared to the overall projects and risks that you might take if you don't do it. So dynamic simulation. Here's two examples. One's a cylinder head block and one's the pistons. Creates a dynamic view of the material flow. Has distances, cost, time variation. Um, Includes dynamic interactions. So fork trucks, workers, production conveyors. You get to see everything that optimizes your line. It lowers the safety risk and optimize line side delivery and inventory levels. So you're not waiting for material or you have too much material stocked on your lines. What do you have to do when you want to do a major change? You simulate it first and then we'll look at it. So how do we do it? So there's 8 major phases for the proper application. We got to define what the problem is. And then we do a design study. So how are we going to fix it? What are we going to do? Then we do a conceptual model. Hey, we're going to add a buffer in between station 7 and 9. Station 8's idle right now. We're going to make it a bigger buffer. Then we're going to do the inputs, the assumptions, process definition. Then we're going to build, validate, and verify the model. How do you do that? Well, we're going to go back to your system. It should match your production as your current state. And then we do the experimentation where we put in the buffer, where we put in the different scenarios. I want to add 2 robots. I want to move a application of glue. Then we document results and we define the last thing you do is define the life cycle. Is this model going to be continuous improvement where we keep doing it? Every model change, we keep upgrading, updating. Um, those are the things that our company preaches. We teach simulation methodology. We, you know, we're one of the founding fathers of our company is a practitioner of this, and he experiences this in the real world every day. So what might the data represent? How events enter and exit the system? So this might be the height of the people in your city, normal, right? Uniform. This might represent the flow of water from a valve. Might represent the school arrival for your class, whether you're early, late, log, normal. These are different um, probability distributions that we have to use. And we look at the graphs and the charts, and it gives us everything. Here's a case study in Simio looking at hospital. So it's not just industrial, it's hospital utilization. Do we have enough family care centers? Do we have enough urgent care? Do we have enough emergency rooms? And we look at the data and we build a process model. Is 24 rooms enough? And then the overflow is beds in the hallway. What do we want to know? Room utilization, number of beds in the hallway utilized, triage, registration. Is our lobby big enough? Is the flow through the area constructive so that we're not mixing and matching and losing patients? It's not one of the things that we want to do is have someone, wait and wait and wait and wait. So this gives you the cue for your triage, your min, max, average, your waiting time for a bed. You get sent to the hospital. You're going to continue on to the main part of the hospital instead of the triage area. You're going to spend a couple days in the hospital. You got to know, how long are we waiting? And then the parking lot. Is the parking lot, this is outside of the building. So we also simulate that. So we know that there's enough capacity, enough time. And that with this case study, we end up with our conclusions. So the industrial Internet of Things, if you haven't heard of it, and I think everybody has, so a lot of us are calling it 4.0, Industry 4.0, it's led to the development of smart factories. How do we do that? Well, we start with a simulation model as a basis for changes. And then we use real world inputs and outputs tied to their digital twin. We want to know, hey, at noon today, I can make a change in the speed of the conveyor because I got an extra person. Can I do it? It optimizes it. The production schedule. Can we run a bit leaner schedule so we're using the employees more than 50% of the time? We're using them 85% of the time. The integration of simulation, statistical analysis, and optimization in the design and implementation allows you to look at the future. I have a crystal ball now. If you think about what's going on in the world, major investments that you do can be digitized, looked at, and prevent major design issues that lead to the cost overruns like Chris Mounts was talking about. We have the ability to help. And with discrete event, that's that middle part of the digital twin progression. And it's a major investment. And you want to get it right the first time. I have clients that are basing $100 million worth of investments on digital twin right now. They want to know, is it cost effective? Does it work? And now we lead into our industrial engineering aspect. And Nick, I believe this is you.
Thank you very much, David. Our simulation team has done some exceptional work, and we have a very interesting twist on what we've been finding. Some of us have been doing discrete event simulation modeling since the mid 1990s, if you can believe it, and we've come a long way since that time. But the consistent factor has been that seldom has discrete event simulation cost anybody anything. And what I mean by that is that the very nature of the work is to find optimizations and provide a return on investment. Classic industrial engineering work of time studies and layouts and material handling and line balancing and so on, all of those things are blocking and tackling and basic work that must be done to set up the line correctly. And then when we get to the simulation piece, it's optimizing all of those elements. at the next piece. I think I can find the right button. There it is. So we have all this historical data representing it, as Dave had shown, in various different models of incoming probabilities. And we set up these simulations, and we think we have a pretty good understanding of what our digital factory, what our smart factory is going to look like and how it's going to perform. And then reality happens. Maybe things don't quite work the way that you intended. Something goes wrong. So in addition to the modeling, to the simulation, we also take it to the next step, and that is to put together a feedback loop. Now, forgive this very simplistic look, but I find it's kind of fun to talk about it. Here we have a perfect digital image of a basketball. But when we drop the basketball, it doesn't bounce. Okay, forgive me, this is PowerPoint, but it doesn't bounce. Why? This is not a digital twin. Okay, if it was a digital twin, the ball would bounce. Okay, and how do we understand that? Well, because you would have to model in the hysteresis of the rubber, the air pressure in the ball, the hardness of the floor. The point of this little fun image is that the digital twin of anything is programmed to behave according to the performance characteristics that the creator is seeking to model. So if we want to have a digital twin of a basketball, we better know what its purpose is. So that's the same thing for all of the work that we do. For example, let's pretend for a minute we're looking at a factory and we have a digital twin in mind. Well, we can't do an entire digital twin of all of the vehicle. Well, you could, but that's a different science. But let's pretend right now that we're talking about a digital twin of the manufacturing process where we're loading doors onto a car. So when I'm looking at just this door, then I need to know some things about it. Maybe the center of gravity, maybe the dimensional contact points that are critical to find this location. Maybe it's the overall mass. I don't need to know the hardness of the steel. I don't need to know who made the regulator in it. If my digital twin is intended to show how I assemble this vehicle and we're focusing on the door, I need to know the performance characteristics of that component or that element that I'm working on. And then the place, the factory that it's being put in, the equipment that is being used, the processes, and so on. So the idea is that a digital twin roadmap is defined by you. What are you trying to accomplish? What are you trying to emulate? And if we're trying to do everything, you're going to choke. You need to identify what is the digital twin you're trying to accomplish and then pursue it that way. Now, when we get into the real world, things go wrong. So we have this beautiful little sensor. This is just one example of the kind of sensors, the size of a quarter, that can tell you about the temperature, the vibration, the pressure. So when things are happening, maybe a part fell off the conveyor, like that silly little rotating box, or something is heating up, or there's a vibration. There's information that's available to you very quickly to connect with the Internet of Things, the Industry 4.0. So when our simulation says, this is how things will run, and now we've got sensors all over the plant that says, hang on, this just happened, or this didn't happen, it was supposed to. We adjust our model so that we adjust what was simulated to reality. And these little sensors are really easy to access, and how we deploy them is up to us. So we have maintenance schedules, preventative schedules, some of the stuff that Chris talked about. But the idea is to get to a predictive maintenance point. And it's not just maintenance, but it's also reaction to what's happening in the plant. So before things fry, break, fall off, we should find out and be able to make smart adjustments. Now, is that artificial intelligence? Is that machine learning? Sure. I don't think we're prepared to talk about that today, but that's the kind of insight that goes into this type of programming. When you and I are driving down the street and we happen to see a ball jump out between two parked cars, we have instinctively known there's probably a kid following that bouncing ball. So we apply the brakes. If we didn't think there was, we'd probably hit the ball. But we know that one thing leads to another. The same thing with machine learning. If we tell them that this vibration is suggesting that there's going to be a bearing fry in about 2 days, we have some information, we know something, we can do something about it. It's just that simple. So here's an example of a complex machine with these kind of sensors put inside of it. And by sensing the acceptable operating parameters of heat, pressure, vibration, and then figuring out when they happen ahead of time so we can keep it running. So from the very introduction of our discussion, we said that the things we do in our smart factory are applicable to smart complexes and communities. The factors are very much the same. Understand what is the layout, what is the facility, what are the processes, what is the equipment, how things are moving and flowing, simulate them, and then get feedback as to how things are changing. When we look at the kinds of integrated services, I really like that one periodic table that Chris put up earlier, that all of the components that go into a digital twin from a manufacturing standpoint, these are high-level items, but we still need to have the services along the bottom. It is a given. It is a given to have software, IT support, engineering in place. We cannot, these are life support systems that are required for us to be able to maintain the world. Whether or not we are doing the cooking or whether you're doing landscaping, you all need basic tools that have to operate every day. And for an engineering digital twin world, these digital tools are required to keep us running. With that, that brings us to our 40-minute plan. And we open up to questions or comments.